Is everyone up for doing a selfie with me? I think it's sometimes fun. Okay, here we go. Okay, yeah, get in. Get in there, Nicholas. Here we go. Thank you very much. Wonderful. Okay, I think I've got the dubious pleasure of being the last presentation of the day. Should I?
That's all that happens.
Thank you, Tina. Shall I come and stand this side so you may be able to see it better? I'm hoping my transitions are a little bit quicker than yours ended up. Okay, so a few quick things. Are we actually up and running? How much is the latency on this? I thought I'd just show you.
It's about 4 seconds.
I just thought I'd show you my little journey. So this is the shortest path I've ever done to Amsterdam. I've typically flown. So this is my direct route from Felixstowe in the UK to the Rye, and actually that was my path. So train to Harwich, then the ferry to the Hook, and up on the train. So that was pretty good. So the shortest path does work, although that bit was quite slow on Wednesday, I think. Anyway, that's how I got here. I've been with a peer for almost a year now. So last year when I spoke on this, I was speaking for a different company, but I soon joined a peer after that. Just want to give one company plug. First of all, I do a regular podcast called Time for Tea with Andy. For those of you that know me, I have a bit of a passion for cups of tea. I'm adequately serviced by the great team here. Also, if you have a chance before you leave, do come and check the Appear booth, which is Hall 1B41. It would be good to see you there. So that's the commercial over, and I will jump into what I'm going to be talking about. So I want to give you kind of a resume of quite a few topics related to time and timing and latency within audio production. So a few people from the history of the world have had some comments on time. I've used some of these quotes before, so it's not new, but I want to cover everything from looking at latency requirements, looking at the criticality of different elements of timing within workflows, including alignment of timing, and also the standards work that's going on. So I'm trying to do a kind of a quick dive into some of those bits as we move forwards. So a couple of generic just placeholders, if you like, for expectations. First of all, what are content producers wanting to do with live production? In my mind, there's always three tenets of what they want to do. They want to reduce the cost of how they're doing stuff. They want to up the production value. So they want to be able to be more creative with the budget they've got. And therefore, they want more flexibility in the way they're going to do things. And also, one thing that's recurring more and more at the moment is personalization. How can actually, that's the main way that people are upping the production value and making it more attractive, more and more so in an internet-based world. So that's kind of where the customer's coming from. This is my very simple live production workflow slide. So everything from the glass at this end to the glass at the other end in the capture, and obviously the whole chain is vitally important in terms of the end user experience. In terms of the production piece, I guess where we are focusing as a company is very much on the post-camera acquisition through to being part of the production processing itself. But that's the workflow that I'm going to be talking about as we go through that. And very specifically, I'm talking about live production workflow rather than NLE work and offline, although the synergy and the convergence of those is interesting. Again, this is a slide you've probably seen before. This is some work we did with the DPP during lockdown, actually, in COVID times, to actually define the different ways people are doing production. So traditionally, this top model was how you did it. Your acquisition devices and your processing and storage and your control were all co-located, either in a studio, in a gallery, or on an OB truck. But now, accelerated by the likes of COVID, but now accelerated with sustainability drives, with maximum use of people, distributed production is here to stay. And many companies are now focusing, big production organizations, on global distributed production, where you have central repositories of equipment that you're using to do the storage and the data processing, your network connecting stuff, and you're sending the minimum possible equipment to site to allow that to happen. And that has implications for, amongst other things, timing. So that's important. And why does it have implications for timing? Because the one non-negotiable in latency is the speed of light and fiber. We can pretty well optimize everything else, although I would deign to suggest that vendors are not necessarily doing that yet, but the non-negotiables there. Actually, if you've seen the gradual rollout of hollow fibre, that does actually take us from 2 times 10 to the 8 up to the true speed of light in a vacuum of 3 times 10 to the 8 metres a second. So there is a 50% advantage which we're not yet leveraging globally because we're still using solid fibre. But that's the only benefit we're going to do unless someone works a real miracle, in which case patent it. Okay, so that's the non-negotiable thing. One of the other big things I want to talk about, and you may have seen this slide I've used before, because this I think is a vitally important bit which demonstrates the real transition we're in as an industry. We are moving from a linear workflow of producing live video, which has been the same for the last 90 years, albeit using different technology over those 90 years, to actually the point where more and more of the actual live production capability is able to be realized in software. And we are, as an industry, on an inevitable journey to this becoming more and more of a software chain of processing elements. We'll talk about some of the implications of that in a minute. But that means that as long as, and this is a very big but, if we have the correct timestamping of all of the media elements that we're pulling in, the video frames, the audio samples, then we don't have to have this curated linear flow of data, which is great if you've got like an analog cable. It's great if you've got a CRT tube that you're scanning, but if you're actually using compute works in burstiness. It just does some math, it shoves stuff across, and we need to make the way we actually do content production much more compute savvy. But that has challenges potentially in terms of timing, and much as I absolutely love 2110 because I was a big part of helping to make it happen, that doesn't really work within compute. It works very well in the linear world on the ground, but not within compute. So we'll come back to that a little bit later on as well. So watch this space. There's quite a lot of initiatives that are happening in this space, and I might just reference them a little bit later on, both in terms of how we get in, and when I use the term cloud on this slide, I mean compute, be that publicly or privately hosted, locally or remote from where you are. We've got quite a lot of work going on getting in and out of the cloud, in and out of compute, but also, most importantly, getting between compute, because this quite often, although it doesn't need to be as a linear process, this absolutely shouldn't be a linear process, a synchronous process in terms of the way it's working. There's lots of initiatives. So jumping onto that latency, the timing, what's important, what's critical in terms of the way we look at workflow. So we fundamentally, if you want to break a live production into some clumps, we've got acquisition devices and things that we're viewing on. So we're looking at cameras, microphones, tally lights, headphones and monitors and monitors, viewing monitors. So those are the things that the edge devices, if you like. We've got processing and storage, which may well be located somewhere completely different. We've got the control surfaces, be they soft or physical. And then we've actually got the monitoring things at the far end. All of those need to be interconnected, and some of those latencies and delays are really critical, and others actually don't matter that much. And what we're going to do is just dive into those very briefly to have a look at this. So what I've tried to do here, thinking about a production, is which things are really critical in terms of timing, which things are not so critical, and which things actually we don't have to be too fussed about as well. Because I think we're over-engineering timing in some circumstances in the way we do stuff. So most critical, I'll start on this side, is phase coherent audio. I don't think there's a more critical part of any production chain than phase coherent audio, because you've got roughly a tolerance of 20 microseconds and you're stuffed. Yeah, so if you've actually got multiple microphones creating a sound field, then you've got to be sample accurate in the way you're actually putting those back. So that top right is our most critical constraint in terms of timing. Also fairly critical, and it's also in the audio domain, is actually local looping back of audio, especially to someone in their ears, etc., that's probably got like a 5 millisecond target, but it needs to be better than 5 milliseconds to make that work. So if you're thinking about me about like this remote production stuff we've been talking about, you know, things like that actually cannot go in and out of cloud infrastructure. Or cannot really even go long distances. That needs to stay local. If we move down to the next level, then we've actually got some alignment stuff. So for instance, cameras. So if you've got a multi-camera shoot, then they need to be frame accurate. Ideally, you want them to be scanning. But if you've got cameras in a high-speed environment like a sports event you're cutting between, then you need that frame accuracy. So we're talking 20 milliseconds circa here as a target there. We've also got the tactility, if you like, is that a word, of human beings pressing buttons and expecting to see something happen as a result of it. Now, actually, the counsel I have from people actually are involved in doing production is you can tolerate a bit of latency there as long as it's consistent. What you can't do is have inconsistency. I'm already learning to work with 4 seconds latency on pressing this button to my changes. And it took a while. It took me 3 or 4 slides to get used to it. So people can cope with that, but only if it's constant. But even so, it's a fairly tight timing requirement. That probably needs to be within 100 milliseconds or so for it to feel right. We then have got 2 different sets of cameras, and I wanted to show you this because, again, speaking to people involved in production, I think this is very important. There are some cameras that you want to get back into your production system where that latency is actually pretty important, because if you think you've got some closed loops here, like because the cameraman sees a tally light, and then you've got the people doing the RCP stuff on the shutter control, etc. And there's a loop there between the people seeing that back at base coming back. So you've got like a timing loop there. And also, if the people are actually doing the remote direction, then you've got to have a fairly tight loop there. But if you think about maybe like a 15, 16 camera production of a sports event, typically probably only 6 cameras are being cut between for the main action. A lot of the others are just being used for replay. So, you know, they're just being used to do the slow-mo behind the goal mouth, behind the goal nets, which you never see cut to live. They're just to show the alternative angles. So actually, we've actually got arguably 2 different speed requirements here. This is where I'm challenging some of our, you know, so we have some which are quite critical, but others actually where, maybe this, and I'll come on to some figures in a minute, because I think I did actually put some figures on here, did I? Somewhere around there, yeah. So we've got possibly, and these are not absolute figures, but these are just my starter for 10s. Audio, phase coherent audio, 20 microseconds is your limit. 5 millisecond for local loop audio, for audio talkback, etc. 20 milliseconds for camera alignment. That's frame-based accuracy there. Maybe 200 milliseconds for the high-speed REMI cameras that need to be in a loop when you're doing a remote production. But maybe some of those other camera angles that are just going into ingest into the replay system and are never likely to hit live, probably you can tolerate up to a second on those without actually having a challenge. And that actually, the reason that's critical is you can actually use different types of connectivity compression maybe on there to actually save cost in an environment. So that's kind of just some mindsets of the way we're thinking on the timing periods and where that's going. So timing references, those of you that are old enough, we've been used to various timing references over the years. We used to dial up to find out what the time was. Did anyone else used to reset their original digital watch on the last pip when you dialed, either the pips received over the radio? And I was absolutely adamant that I would never go to streamed audio on radio, because it means the BBC Radio 4 pips in the UK, you listen to them maybe 15 seconds late. But actually, I don't really care anymore. It just happens, and I accept it. And we don't do any off-air received audio at all in our house now. It's all streamed. So we get used to those timing offsets as long as they're not critical to our lives. Keeping everything in sync is, however, a challenge, and that's something that we've just started to use different technology for. So we used to gen lock our cameras and all the other pieces of equipment in the system, which was basically giving them a common reference. So everything is frequency and phase aligned by doing that. We now use some kind of GNSS reference typically, although people are still talking about the relative security of that, etc. But most things are GNSS referenced. I'm going to challenge in a minute the level of timing accuracy we need within the workflow, but the timing of the acquisition is still very important, because if we've got, going back to my microphone example, if we actually have a number of, say, 5G connected microphones that are forming a phase coherent sound field, then those microphones need to know what actual time is to 10 microseconds accuracy, or else you're not going to be able to synthesize a stable sound field from there. Slightly more tolerance with the video, but those are the requirements that we have when we're running through these things. So typically we take timing and reference and distribute it, and actually we're just doing a similar thing there. Reconciling time. So what we have done, the adventure of 2110, the thing that we were trying to do, and we've had pretty good success with that, is actually saying we don't want to take an SDI feed where we've got 1.5, 3, or even 12 gigabits per second of data, and feed that into the audio console just so it can extract a few 2 meg audio channels. It's much better if we actually create content, we actually have a timestamp on all of that content. The audio goes on a relatively low speed network, goes into devices that only need to handle maybe up to 100 megs or a few hundred megs of data, whereas the video can go into stuff that can cope with 100 gigs worth of data, be processed, and we will reconcile it downstream. Now, one of the things, and some of you have heard me preach about this a lot in the last 3 or 4 years, one of the things we really messed up on with 2110 was actually defining the way we actually reconcile those essences, because what happens is, by intention in AES67, and therefore by ripple through on the way we did 2110-30 and 2110-20 and then 40, a lot of things restamp time, and we actually lose that all-important nugget of information, which is the origination timestamp. Credit to the BBC, in the draft work that they did before we developed TRO3 and then 2110, they actually had a separate field for the origination time. And more use cases are coming up now where people are saying we need to carry some metadata that allows us at least to reconstruct origination time. So at any point in the workflow, we can actually reconcile and align things. This doesn't just apply to the live workflow, but if you think if you're doing a multi-ISO record to do a playback later, even if you're doing multi-camera angles of a sports event, you want to be able to play them back in synchronism as well. So it's not just the live workflow timing, but it's actually then that timing information being recorded, so when you replay, you can actually do that alignment as well. Anyway, I've done lots of talking on that previously, so I will leave you to do that, but there is still some work in progress happening with that. Now, this is the point the latency's caught me out, because I'm sure I pressed this button about 7 seconds ago now, and we still haven't transitioned. Let me try again. I'm just going to see if this works. Okay. End-to-end metadata. So this is actually important not just for timing information, but more and more people are seeing the requirement for metadata where we actually need to be able to send information, and it might be information about the native spatial and temporal resolution of the original capture, because if we go through transformations of video and audio as we go through a workflow, it's sometimes really good to know, was that originally 10-bit, 12-bit or 8-bit video that we actually had? What's happened to it en route? So things like that are also very important. Have I run out of time, Lee? No, we're
back.
okay, this is good. I'm just panicking that we might be out there.
I appreciate that, though.
Cool. So we have some things that are actually making things a little bit harder, because, as I've alluded to, we've potentially got things like 5G acquisition running in parallel with traditional fibre or cable connected infrastructure. So there's some timing uncertainty which we need to buffer for there. We've got more and more compute happening in the middle, which has a much more non-deterministic time to actually produce the results than we used to. So we have to budget for what we are calling, in some of the work we're doing in VSF, T99, but basically T-max. What's the worst case that the compute is taking to actually achieve that. And then we need to do the maths to sum that to where we get to. I think I'm going to whistle through this. You're aware of the STA2110 suite. Just to say, we're still doing some work for a new part called 2110-11, which is all about how we actually propagate some of that timing information. And we did do some revisions to -10 the year before last, which actually goes some way to actually doing timestamp preservation. There's more on that in some of my other talks, and send me an email if you want to go through that. Just looking at timing planes, because this is what we're calling the work we're doing in SIMPTE very briefly, just this one slide on this. There are some timing planes we intentionally introduce in live production. We may intentionally say we want a profanity delay. We're intentionally to delay the whole program before emission for 5 seconds or 10 seconds for profanity. If we've got remote control surfaces, we know we may have a non-negotiable 300 millisecond round loop to do that. We may have an augmented reality set, which costs us maybe half a second in the VR synthesis that goes alongside. So we've got a whole load of cameras that are straight time, but we've got other cameras that have effectively got a half a second lag before we can put them into the system. So all of these things have to be taken into account before we do the final tape layout. And it's just obvious that all of these offsets should be able to be handled automatically. It's just numbers we're handling with, and we really haven't got there as an industry yet to actually doing so. That's really important. I think I've already covered this, talking about the fact there's a variability in compute processing compared with traditional appliance processing on the way things are handled, and we have to do that Tmax there. And this Tmax, and just to pull this out, courtesy of the GCCG work we're doing here, that Tmax obviously accumulates. So those uncertainty factors, you have to allow the accumulated aggregate maximum of those things as we actually go through the system. Okay, another little thing I want to lob in here. I know various both public and private software cloud providers are advocating and are flagging that they soon will be able to do PTP in cloud. I would argue very strongly you don't need that accuracy of timing within cloud infrastructure. If you think about all of those bits that I talked about, the critical thing is the acquisition. As long as we timestamp on the acquisition devices, both the audio and video time devices, once we're within the compute, most of what we're doing is maths on saying this frame with this frame with this frame, or this audio sample is actually the coherent sample with that one and that one. Or we can align them numerically, do the math, whatever that is, to do the crossfade, to do the effects, whatever you want to do. NTP, in my opinion, is more than sufficient within compute infrastructure to do what we need. When we come back to linear 2110 worlds, we then need to actually have some buffering that can synthesize as a boundary point back into PTP world. But compute doesn't need to do very, very high precision timing. It's just doing maths on accurate numbers it already has. And I think that's a really, really important part. Just talking about other timing things, you may have seen that there's been a couple of different standards that are being used here for JPEG XS. Just as an example, JPEG XS is a mezzanine compression, roughly maybe something like a 6:1 or 8:1 compression that's being used for very high quality, very low latency compression for production. The actual compression decompression cycle is less than 1 millisecond. So if you're long hauling, the compression element is negligible because it's just so far. We're actually using two different ways of carrying that within the infrastructure. TR08 is the way we do it if we're in a PTP-enabled environment where we've got, if you like, ground-to-ground timing references where we've got GNSS referenced phase and frequency accurate timing. TR07 is more like it is transport stream based. It's like MPEG transport streams we've been handling for the last 25 years. And basically, that's what I call forward clocking. You can recover the information from the system. So you don't need to worry about phase coherent locking and frequency coherent clock recovery at the far end. You can recover it from the stream rather than needing to have the same timing reference at the other end. So these tools allow us to service different elements, and possibly the reason we're seeing a lot of use of TR07 in cloud infrastructure is because that means you haven't got to worry about PTP referencing in the cloud as you go in. I'm going to jump through that because that's just a bit more explanation on timing. I am going to throw in another grenade here. As we've gone through 2110 and also in compute, the way people are solving a lot of timing issues or potential timing issues is by adding lots of frame buffers in. So a lot of people are designing things by actually saying, as I receive a thing, I'm going to do a full frame sync. As I push it out, I'm going to do a full frame sync. If you concatenate that over maybe 7 processes in a production life cycle, we've suddenly added 14 frames of delay just to allow us to synchronize. Most of them are completely unnecessary in the process, but people are doing it, dare I say, I think out of laziness or just safety that's unnecessary. And that's applying both in 2110 ecosystems and in compute software design. And I would urge people in the industry to actually get their act together and only introduce necessary latency. So fundamental challenges: we have linear connections like 2110, like SDI. We have this non-linear compute-based way to workflow. We need to sort out capture time. We need to be able to track time as it's used through the system, and we need to be able to optimize that by decent design of the way we do things. Okay, that's been a real whistle-stop talk. Hopefully it's given you some nuggets. The idea was only to get you interested in things. I'm always at the end available on my email or on the phone if you'd like to actually talk to me at any point. And my offer, which Mr. Wes Simpson took up last week, if you're ever in the UK, come over to my house and I will make you a very nice cup of tea. So that's it for me. Do we have any questions or observations?
So it works, yeah. So as I understood, so tier 07 will be very helpful to transfer the streams to the cloud, and tier 08 works when there is PTP. But inside the cloud, when different systems have to communicate between each other, so what's there the best technology choice? Or?
Excellent question. So both TR07 and TR08 are what I call streaming interfaces, like NDI is, like SDI is, like 2110 is. And in fact, TR08 is part of 2110. It's 2110-22 is what TR08 is. In compute, we shouldn't be using linear streaming interfaces. We should be using native compute-friendly data handoffs. The only thing that's been published in the world, and there was a reference back to it, I didn't call it out on one of the slides, is the work the GCCG has done. It's on GitHub, so if you look at the GCCG work on GitHub, I wonder if I can just backslide to that to show you that. It was fairly early on. It's going to be very slow with this because of my 4-second latency each time. But there's some... basically a draft has been published already, and this is a native asynchronous compute interface. Now, 1 or 2 vendors are doing something like that internally within their closed ecosystems, but the GCCG work is the first work where we've published as an industry something that might do this for us. We're not claiming it addresses everything yet. It's a draft and it needs more work. We as a peer have just implemented a prototype of it and it looks pretty good. But yes, we don't want linear streaming interfaces within compute. We want to be able to do native asynchronous handoffs. Yeah. So this is a clump of data. It's the next 4 video frames, or it's the next 47 audio samples. Probably not 47. Let's make that 48. And we're going to dump that across, and that's what we really need to have within compute. So check it out on GitHub. And if you look at the VSF, you can see we've actually published that. But message me if you can't find it. I'm just whistling back now to see if I can actually find the slide with that on. I think I put it quite near the beginning, which is unfortunate with the latency I'm experiencing here. So I'll keep whistling back. I'll put it up at the end so you can find it. Any more questions or observations? There's a very silent man at the end there that I expected to throw some kind of grenade in, but he's just sitting there respectively. Go on, one last from Ed.
Give us a preview of Dash 11 then. How are you going to solve the problem of the origin timestamp? What's the recommendation going to be?
So what we say in dash 11, which is the work that GCCG is doing, is basically you have to maintain that acquisition time, and you carry that as information. The thing is, the reason people, even within 2110, have existed and managed to exist without propagating origination time is because if you've got like a hose pipe effect where everything, you push through like 30 centimeters of water, and then the next 30 centimeters of water comes through, and the next 30 centimeters, then everything you can do relative. But if you're just lobbing stuff into compute and it's doing maths, you have to have timestamps. Otherwise, you haven't a clue what the hell's happening. So we prescribe that you absolutely have to have timing. Now, there's two ways of doing that. Ideally, what we say in TR11 is you take the origination timestamp as came from the ground. So the original acquisition timestamp from the camera. Failing that, what you do is as it hits the cloud, you create timestamps on acquisition into the cloud. So as it comes in, and then you give the ability for offsets to be applied to allow for the differential latency, which will hopefully be static between the different ingress points. But ideally, and there's still more work to do on this to make sure that things like TR11, TR07 transfer timestamps in an accessible way through there. But thank you for the question, very pertinent.
Does that mean preserving RTP timestamps or introducing header extensions? Yeah.
Well, because we're talking about data file worlds, we're actually taking effectively what was the RTP timestamp and converting that into a usable timing reference. Whether we should go for header extensions in a linear world, I think that ship has sailed, and I say that with a very heavy heart. And the reason it wasn't done is people thought it'd be too hard for FPGA implementations, which is very sad. So, we must have gone past it now. That's interesting. I will find this reference in a minute. But so I think the header extensions, but we are looking at saying there's an additional standard which hasn't really been used yet, dash 41 in 2110, which is a fast metadata channel, which allows you to send maybe even allows you to send frame accurate information. So one of the suggestions is we occasionally send metadata which has the relevant offsets between the current timing reference you've got and the origination time. So you can actually carry enough information for you to derive in origination time. It's a little bit messy, but within the compute world, when we do the data handoff, yeah, we are absolutely saying you have to preserve origination time, even if it's only origination with respect to the ingest point to the compute. Hopefully, it's actually the acquisition point of the microphone or camera. Okay, is that good? I could talk forever, so I'll shut up now. Thank you for your time. It's been a pleasure talking to you. Here we go. There's the GitHub reference if you want to grab it.